In the previous videos, I said we would tackle this particular case in this video. Remember that A represents the number of people depositing money, B the amount of deposit, C the number of people borrowing money, D the amount of loan, and E the amount of cash the bank initially has. This set of conditions can then be interpreted as follows. A equals C, meaning that the numbers of people depositing and borrowing are the same, while B equals D means that the amount of deposit and loan are the same. The bank originally does not have any cash. Under this scenario, the exact amount of money does not matter as long as it is the same. All we need is to ensure that the number of people depositing money is at least the number of people borrowing money at every point of the queue. All that means is that there is actually only one variable affecting the number of ways of queuing. Let's call it n. Then denote the number of ways to queue up the customers to be C with subscript n. This is because this class of numbers is called the Catalan numbers, named after, Catalan, a French-Belgian mathematician. We know that Cn has to depend on n, so it is a function of n, where n is a non-negative integer. The point is to find the function, specifically expressing it analytically. In other words, expressing explicitly in terms of a finite combination of other recognizable functions. Finding the function analytically is sometimes not doable. An algebraic example would be to let f of n to be the smallest positive root of an equation. If you want a combinatorial example, let the function to be Rnn. In the world of combinatorics, this can mean at least two different things: Ramsey number, or the number of self-avoiding walks in an n times n grid. There are links in the description explaining what those terms mean if you are interested. Luckily, the problem is somehow simple enough to have an analytic form, so we are going to derive that. An important realization is that who you put in the front can affect who you can put in the back. This realization might make you want to try using the tree diagram to analyze the entire situation. To avoid taking up too much space, we use a blue upper branch to denote that the next person is borrowing money, while a green lower branch is used to denote that the next person is depositing money. From what we discussed, the number of green branches should be at least the number of blue branches at any point of drawing the diagram. The bank does not have any cash initially, so the first person has to be depositing money. Even if there is only one branch, we also draw it in our tree diagram for consistency. The next person can be either depositing or borrowing money, so we have two possible branches here. If there are only two customers, then this white path shows the only possibility, that the first one deposits and the second borrows. If there are more customers, we can move on. For the upper branch, the next customer has to be depositing money because the bank now does not have any cash. For the lower branch, we can have two branches because in these two cases, the number of green branches still exceeds that of blue ones. Notice that we have a junction here. These two paths are of course different and they represent different ways to queue up the customers, but they have something in common. There are two green branches and one blue branch each. And by utilizing a tree diagram, we show that there are only two ways of queuing the customers up if there are two depositing and one borrowing, which are shown by these two different paths. And this is true for all junctions that we can draw. The number of paths leading to a particular junction equals the number of ways of queuing up the customers of a certain configuration. And that is a fixed number depositing and a fixed number borrowing. And again, if we move on from the junction, then we can have whoever to queue up after that, because the number of green branches will have to be at least that of the blue ones no matter what, and we can continue this process forever. From what we see, it seems that there is a hidden horizontal line that does two things, barring any paths from crossing it, as well as containing the points that are the destinations of the paths. That is because the line contains points where the number of green branches and that of the blue ones up to that point equals, which is what we are caring about. So Cn can also be formulated as the number of paths from the nth point on the line, except for the first one, like C1 corresponds to this point, C2 corresponds to this, and C3 corresponds to this, and so on. Finally, let's rotate all these counterclockwise by 45 degrees. Then the paths going from the bottom left to the points on the white line are called dike paths. The question then becomes how many dike paths are there for a given point on the white line. The reason we turned the original problem into this one is that it is much easier to visualize than manipulating the queues. But then, how do we solve this problem then? In this video, we are presenting one of the many solutions, and some of the other solutions will be presented in the next video. The reason why there are so many solutions is that there are many combinatorial interpretations giving Catalan numbers, including the triangulation of a polygon. And some solutions make sense in some interpretations, but don't in others. And some solutions do the opposite. It's worth reiterating the reformulation of the problem. We want a path from the bottom left to the top right. We can only travel in two directions, up and right. And one more restriction is that the path cannot go above the diagonal line, and we want to find the number of paths available. To solve this problem, let's tackle an easier case and drop the restriction of the diagonal. There are n steps in each of the directions in order to get to your destination. If we forget the visualization for a moment and treat all the different paths as a sequence of ups and rights, then it is easy to see that out of those two n steps, we have to choose n slots to put the rightward steps. The other slots would automatically be the upward steps. And so, there are in total 2n choose n number of ways to go from the bottom left to the top right without the diagonal restriction. But of course, this isn't Cn. Among those 2n choose n paths, there are of course some good ones, but there also include some bad ones. So in the calculation of Cn, we need to subtract the number of bad paths from 2n choose n. But of course, we need to see how to calculate the number of bad paths. So we see a bigger picture. We add one row at the top. We also start off with 0, 0 and end at nn, and this does not change. For any bad paths like this one, it has to touch or cross over this orange line at least once. We considered this part of the path after touching the orange line and reflect across the line. The thing about this method is that we can always reflect back to where we started, so we have established something called a one-to-one correspondence, or a bijection if you want some mathematical jargon. That means the number of bad paths equals the number of reflected paths. It seems silly to write it out, but it allows us to focus on counting the number of reflected paths. Now, since the endpoint of the original path is at nn, the endpoint of the reflected path should be at n-1 n plus 1. If we again take a more systematic look at the whole situation where we view a path as a sequence of ups and rights like this, then we have again 2n steps, because what we have done is reflection and the number of steps should not change. but we have n-1 slots for the rights only. This is because the x-coordinate of the endpoint is now n-1. So now the number of bad paths is exactly 2n choose n-1. In summary, Cn equals the number of both goods and bad paths, which is 2n choose n, subtracting the number of bad paths, which is 2n choose n-1. Some people would have an algebraic treatment to that and figure out that it is a fraction of the binomial coefficient. In one of the other derivations of the algebraic forms of Catalan numbers, we will attempt to explain more naturally where the 1 over n plus 1 comes from. If you enjoyed this video, give it a thumbs up and share it. Don't forget to also subscribe with notifications on so that you get notified when a new video comes up. See you in the next video. Bye!